Hi, this is Chris from MDPI Encyclopedia. Today we're delighted to welcome Professor Dr. Saurya Das, an editorial board member at Astronomy, to talk to us about his research on quantum gravity. Welcome, Professor.
Thank you, Chris, for having me here.
To begin, our audience would like to know more about your academic journey. Could you please share a brief overview of your research background and what drew you to theoretical physics?
Thanks for the question, Chris. So, uh, well, my academic journey began around high school. I got really interested in physics. What interested me most was, I guess, the simplicity of things. There are very few simple laws which are intuitive, which is easy to accept. You can start with, and then explain a host of phenomena. So you explain a lot with very little. That's, I think, what fascinated me. Anyways, I was quite motivated. So I did my undergraduate and master's studies in physics in India. This led me to pursue a PhD in theoretical physics at the Institute of Mathematical Sciences in Chennai. Following this, I did a couple of years postdoctoral fellowship at Pennsylvania State University in the United States, and then a postdoc at the universities of Winnipeg and New Brunswick in Canada, following which I joined as a faculty member at the University of Lethbridge in 2003, and where I'm now a full professor. Over the years, my research has focused on quantum cosmology, quantum gravity, quantum foundations, general relativity, black holes, and foundational questions in physics, and in particular, how a theory of quantum theory of gravity can be formulated, and its the evidences that it might be able to provide to test the theory. So that's been a focus for my research for a long time. Thank you.
Astronomy is a very prominent journal in the field, of course. What motivated you to join its editorial board, and how do you see it contributing to advancements in cosmology and quantum gravity?
Again, thanks for the question. So, yeah, a few things really. Well, firstly, it's a top-rated journal. That's of course the case, but also it has a broad scope. That's what attracted me. It's not too narrow in scope, and I'll say why that's important, I think, and also kind of committed to high quality and accessible research. High quality ensured by rigorous scholarship, peer review. It's international peer review process. It's an international journal, so the standards are very high. It's kept high. The scope is broader than some other journals, maybe, and I see that as a strength because now with increasing connections between various disciplines such as cosmology, theoretical cosmology, observational cosmology, theoretical physics, quantum foundations, even quantum technology, quantum sensing. So it's important to have a forum, again, a forum which promotes high quality of research, but it also a forum or a platform where there can be dialogue between these various interestingly connected disciplines. So these are some of the, well, couple of the things which attracted me to this journal, and I'm very happy to be on the editorial board of this journal. So.
Quantum gravity remains one of the most profound challenges in modern physics. What key unresolved questions in this field drive your research?
Right. So we're in an interesting time in terms of physics and astronomy because we know the most about the universe right now than we ever did. On the flip side, there are also a few fundamental and new fundamental problems which have cropped up, of which we don't know nearly as much as we would like to. So some of the problems which kind of drives my interest and that of many others are the problem of singularity, meaning the initial singularity or the singularity at the center of a black hole. The singularity basically means that we don't have a good theory to predict anything, so our theory breaks down, and that's certainly not a situation where we would like to be in. So that's one of the problems. And a couple of other problems, for example, the problem of dark matter and dark energy. So now we know about 95% of our universe exists in a form whose like kind of broad properties we know, but we really don't know what they are made up of, namely dark matter and dark energy. So these are the some of the main problems, I think, and there are a few others as well, for sure. And quantum gravity, I think, can potentially play a role in every one of them. For example, in the case of singularities, it's kind of self-evident because singularity is a singularity in space-time. So that's well within the realm of quantum gravity. Even the dark matter, dark energy problem, there could be, for example, quantum gravity effects, which can account for part or some of them as a geometrical way or some other way. So quantum gravity, I'm almost certain that it's going to play a role, and quite likely a significant role, in the resolution of these puzzles.
Could you discuss the evolution of theoretical frameworks in quantum gravity? For example, string theory and loop quantum gravity, and also how recent developments have shaped our understanding of space-time?
Right. So I suppose one started with very similar objective, which is to have a consistent quantum universe, and gravity not being quantum really stands out and unlikely to be the case. So that one starts with that thing. So try to quantize the theory, and then there are as many approaches as there are number of proponents. Let's say so. So then there's few avenues which evolved or started and evolved. String theory being one of the most prominent for sure. Loop quantum gravity being another of those approaches, and there are quite a few others. They all have their strengths and weaknesses. They have their pros and cons. So I think that all these approaches have developed quite a bit, have evolved and developed. So that's their strength, and they have quite a few results in, let's say, in terms of black hole entropy or writing gravity in terms of a field theory. So there has been quite a bit of understanding and insight. However, so those are the strengths. On the weakness side, I would say that the connection between these various approaches, at least to me, seems like far from as ever. So the hope was, that if they're all describing the same theory, you might be able to go from one to the other in some kind of duality or whatever. But that doesn't seem to be the case yet. And the other weakness, I think, is the absolute lack of experimental evidence. So of any of these theories, to be honest. So to come back to your question, I think they've shaped the understanding, the future of research, like students who come into this research, and it has trained a lot of people in these disciplines. But I think there is ways to go, and it's not clear to me, at least, that which, if any, would turn out to be the correct theory of quantum gravity.
Moving on then, cosmology and quantum gravity intersect in areas like the early universe and black hole physics. What are the most promising observational or theoretical avenues to test quantum gravity effects?
Right, absolutely. So, of course, as we discussed, it's very important to test those theories. Otherwise, one can have a very excellent, elegant theory, but it needs proof. So coming back to your question, I think there are few avenues again. One of them is better observation of the cosmic microwave background radiation. That's already something people are thinking about and considering and working on it. So that would be one. Gravity waves is the other one. And gravity wave observations, gravitational wave laboratories or interferometers, they have been becoming better and better. The laser interferometer space antenna, or LISA, is in it's a advanced developmental stage, which will go up in the sky, right? So gravitation waves, that would be the second avenue, because they're extremely accurate, sensitive observations, and you need that absolute sensitivity for testing quantum gravitation theories. And the third, I believe, the third avenue would be laboratory-based experiment, and I've worked on some of the theoretical aspects of these and the others as well. So there's quite a bit of possibility. Again, the reason being that the laboratory-based experiments in condensed matter physics or surface physics or quantum optics, they are extremely accurate now, very precise. Their sensitivities are very, very high, to the level that maybe even testing certain predictions, robust predictions of theories of quantum gravity, they might be testable in the laboratory, say a few years down the line. And I think I'm being not over or under optimistic. That's probably the scenario which I think is likely to happen. So.
Well, coming from the, shall we say, existing research, there are different models, and some models even suggest quantum corrections could alter classical cosmology, such as inflation and dark energy. So, do you think that quantum gravity could provide alternative explanations for these phenomena?
Yeah, I do. And again, from two sides. Firstly, it's always possible that it can, but also the more traditional particle physics like theories of dark matter, dark energy, they are promising, serious, and all that. However, again, we are waiting for evidence, right? So if a dark matter particle is observed tomorrow, then of course that's where it is. But it still remains to be observed, which means alternative explanations are essential to explore, and quantum gravity or modifications of gravity, theories of quantum gravity play a role there, because what we see, dark matter, dark energy, well, something is there, observations are there, but the explanation may or may not be in actual physical, particle physics like entities. It could be a geometry which shows up as those, dark matter, dark energy. And if it's geometry, it's within the realm. I mean, it could be a quantum version of geometry, and thereby it's automatically within the realm of quantum gravity. So, in short, quantum gravity effects may be able to account for part or whole of the dark matter, dark energy that we observe in nature, in principle.
Debate continues on those topics, and one current topic of debate, of course, is whether quantum gravity leaves imprints in cosmological data, for example, CMB anomalies and gravitational waves. So, what are your views on detectability, and what future experiments hold potential?
It's a great question, Chris. Thanks. So quantum gravity effects. For any theory of quantum gravity or quantum cosmology, there must be some detectable effects. Otherwise, how do we know that the theory is correct? That's the first one. Secondly, we do expect those effects to be very small for two reasons. Firstly, because gravity is very weak and quantum gravity effects would likely be even weaker. And if they were not weak, we probably would have detected them by now. So obviously, we expect them to be very weak. However, on the bright side, these future gravity wave detectors are the ones which are currently, they're amazingly sensitive instruments. They can detect, effectively motion, which is like, 1,000 part, size of an atom and that kind of thing, and getting better in terms of their usability, their applicability, their frequency range and everything. So therefore, of course, the predictions from quantum gravity theories has to match up with the experimental capabilities, but I do see concrete hope and also evidence, if you like, that this quite likely would happen, which means that the future gravitational wave detectors, for example, would be able to measure these effects, as well as, future CMB observations, and as I mentioned, even some tabletop experiments as well.
As one final question then. Inherited or fundamental physical constants, for example, the cosmological constant, are often seen as fine-tuned. Do you believe quantum gravity could offer a natural explanation for these values, or must we appeal to multiverse theories?
Yeah, well, it's intriguing, right? It's that these fundamental constants exist and we don't have a better explanation for them. And as you mentioned, it's the cosmological constant. You can add to that the Newton's gravitational constant, or the speed of light, or h bar, the Planck's constant, and those. So we obviously would like to have an explanation for them, right? Why is the speed of light what it is and not something else? So we would like to have an explanation for that. For the cosmological constant, for example, multiverse theories offer one way. However, I would perhaps prefer to explore whether quantum gravity could yield more fundamental and dynamical explanations. For example, the vacuum energy contributions, which we know could contribute to dark energy, except it mismatches by astronomical amount, right? So quantum gravity could possibly cancel some of the vacuum energy and bring it in line with what's observed. So yes, the answer is yes. I wish there was a better or more clearer pathway towards that, but that's part of what our research is about.
Absolutely. Well, thank you so much for your time, Professor Das. It's been an absolute pleasure speaking with you today.
Thank you, Chris, for having me. You have a great day.